So, hello everybody, welcome to today's webinar. I'm Enrico Scoccimarro from the Euro-Mediterranean Center on Climate Change, and I'm going to present and to show just a few slides regarding the CMCC Center, and then we will jump on the talk of today that is led by Dorotea Iovino, and is on the benefit of the increased resolution on the North Atlantic Ocean dynamics. But just let me spend a few words about the center, and then we will introduce better Dorotea and this webinar today. The Euro-Mediterranean Center mission is to investigate and to model our climate system and its variability and interaction with the society for the provision of scientific results that can be used to stimulate sustainable growth and protect the environment and develop the science-driven adaptation and mitigation policy in a changing climate. The Euro-Mediterranean Center is a sort of network distributed throughout the country. We have different centers in Venezia, Milan, Bologna, Viterbo, Caserta, Lecce, and Sassari. And there are different research divisions moving from the advanced scientific computing devoted to the support of our activity of climate modeling based on the computing center that we have at CMCC located in Lecce. There are also the division devoted to the simulation of the climate in its different components, the atmosphere, the ocean, and at the different time scale and horizontal resolution needed. So from the general circulation model to the regional models, and from the long-term simulation to the short-term prediction, seasonal and decadal predictions. There are also divisions devoted to the analysis of the impacts from the economic point of view, but also related to the risk assessment and adaptation strategy, and so on and so forth. So we are covering at CMCC all of the aspects dealing with climate change and variability and the impacts. And this is the list of the topics that we can that we touch, and there are also many information on the web page of the center related to these topics. And finally, we provide the information. All of the information that we produce at CMCC are disseminated through different communication strategy, participating to different educational programs, events, and also through scientific peer review publication and participation to different conferences around the world. So now let's focus on the today talk. First, there are also few words to say about the technicalities. So your audio and video are deactivated, and you need to intervene or make a question only through the Q&A section. So you can write on the Q&A section. This is the preferred solution, and then I will make the question on your behind to Dorotea, or you can also use the raise hand feature if you want. This webinar is going to be recorded and uploaded to the CMCC YouTube channel, and if you have any question about the webinar and the rules, you can email the webinar address. Well, after this, the next webinar will be in October 5, and will be related to the Sustainable Development Pathway for Climate Action within the UN 230 agenda by Björn Sergel, and this is something that we are going to have in more or less 1 week. But now let's jump to the today talk by Dorotea Iovino. We are going to talk about the benefit of increased resolution on the North Atlantic Ocean dynamics. Dorotea is currently a scientist here at CMCC, and in Bologna. She is part of the activity of the Ocean and Sea Ice Modeling Group. She is leading this research activity, and she holds her PhD in physical oceanography from the Geophysical Institute at the University of Bergen in Norway. She expanded her knowledge and experience in oceanography and numerical modeling during the postdoctorate at the L'Océan in Paris, and for the last 15 years, she coordinated and been involved in several international and national scientific projects, working on ocean and sea ice modeling, both from the technical and the scientific, covering both the technical and the scientific aspect, with a particular interest in the high-resolution ocean sea ice modeling. She is member of the Clever Click and the Clever Ocean Model Development Panels since 2017, and she collaborates with the NEMO system in the developing of the model system, and she is the CMCC expert and member of the NEMO CI's working group. She also teaches at both the PhD program in Science and Management at the Ca' Foscari University in Venice, and the PhD program on Future Art, Climate Change and Societal Challenges at the University of Bologna. So I don't have enough time to say something about the talk, but Dorotea, please go ahead and let's start with this really interesting talk that we're going to have today. I'm going to stop to share my screen. Dorotea, can you hear us?
Yes, I'm going to take the screen. Hope you see the presentation. So as Enrico mentioned, today I'm going to discuss if and how ocean resolution into the North Atlantic mainly is affected by modification into the climate model system that we use to simulate it, of course. And specifically, I'm going to focus on the role of the horizontal grid spacing into those systems. Why the North Atlantic? That's mainly because the ocean circulation in this region is central for modulating the Northern Hemisphere climates, but also the global climates and the impact of the ocean on the complete system is absolutely high, and mainly comes from the dynamics into this area. So if you want to assess the risk caused by climate change, even on the European region or over Italy, is essential to understand and to properly reproduce in numerical simulation of the variability of this sector of the ocean. And then I want to mention that all model results that I'm going to, or most of the model results that I'm going to present for this talk comes from the European project called Primavera, the CMCC collaborating with, and most of the results actually are part of the study leading by colleagues into the project. Names are included here, listed here on the slides, but there's a really long list of people that worked with these results and still using Primavera results. So if we go on the simulation here, one key point in Primavera was to coordinate the common multimodal experiments. I don't know if the connection is still fluid. Anyway, I'm going on. So what Primavera actually did is to coordinate one of the MIP experiments into the CMIP environments. Mainly the experiment here is focused on the high resolution systems, where the high resolution is for all components involved into the climate and couple model. And of course, for doing that, so in setting up this HighRes MIP exercise, we need to establish a protocol, a common and coordinated protocol, and that was, of course, part of the of Primavera. There are a bunch of different simulations that will be run. We are going to focus on the couple ones today, and the way that actually this multimodal, multi-resolution ensemble is be run is to follow the design that we have here on the schematic. So we had short spin up at the beginning, forced by constant atmospheric forcing. The spin up started in 1955 and lasted for 15 years. And then this provide initial condition for the next type of simulation, both the control runs and historical runs. For the first case, we had simulation of at least 100 years. For some institutions, that's even longer. With the constant forcing again, while we had another branch of simulation, the historical one, that had time varying external forcing covering the period from 1915 to 2054. And we are going to use both kind of runs into this talk. but I will also present one slide of what is called future simulation. So using external forcing for future scenario, we also run a simulation from 2015 to 2050 to cover a projection in the future for the climate system. So the point actually in having high resolution is justified for many previous study, and mainly for the caveats that we have highlighted in previous modeling study. So it's kind of clear that mainly for the ocean, some of the key processes that we need to properly simulate are not adequately reproduced when we run CMIP-like exercise with low resolution into the ocean. Of course, both sea ice and atmosphere are part of the story. And of course, we need to increase the complexity of the system. So the physical parameters, parameterization into the model, and Primavera also did part of that. But mainly today we're going to focus on the role that increasing simulation has in this kind of exercise, and what we can gain in our understanding when we make this kind of exercise. So if I manage to go to the next slide, here we have a list of the global climate models that I'm going to compare today. Mainly I will focus on the bluish part of the plot, because those are run, that comes all from Primavera projects, while we also have an extra simulation that has been provided by the Anchor with the model following very similar protocol, but was not part of the project in details. There are, of course, different institutions involved here. I will always use over the slides the name of the model to identify the product that I'm talking about. What we can focus here is mainly the diversity or the similarities that we have within the system. So if you see the mouse, if you look at the model components, we have first line indicating the atmospheric components, then the ocean component, and the third one is the sea ice model included into the system. So for the atmospheric component, we have large diversity. There are only two model systems, like the CMCC one and the Anchor one. The Anchor one, they share the same model, even though the version of CAM are totally different. So the complexity of the two atmospheric code is different here. If we move to the ice, so the third line, we also have large variety of different codes. Size is present in 3 different systems. For Anchor, we have size 5 into this simulation, so is advanced compared with size 4 used by UK and CMCC. But also in this case, actually, the size 4 that you see here in CMCC case come as the original version released by Los Alamos, while the one used into the UK system is actually the version released by CPOM. So physics is also different into this code. For the ocean, the situation is slightly different, because we have most of the effort coming Primavera from the European institution. So the name that you see repeating here is the European model, the Community European model. So it's NEMO. They is present in 5 of the systems here, and also with the same version of the code. So we all updated NEMO to the version 3.6 for this exercise, even though the physics inside the model is not shared. So there could anyway be differences into the model result, and then you will see that that's the case. For the resolution, that is our main point here, we see that for the atmospheric part and for the ocean too, we go from 100 kilometers into the low resolution system up to a few tens of a kilometer for the atmosphere, for example. For the ocean, we can generally say that we have low resolution components. They are at 1 degree of resolution, so about 100 kilometers. Then we switch to, and then we would call that not adding ocean. And then we move to the 1/4 degree generally, that is called eddy permitting configurations. So that means that the equator, wherever is the grid shape, when we move away from that, the nominal resolution is about 25 kilometers. And for some cases like NCAR and the UK models, we also have a higher resolution into the ocean. They are of the order 1/10 of degree. And then there are other two peculiar cases like MPI, CMCC, where the ocean resolution is actually kept constant to 40 kilometers and 45 respectively, but there is a change into the atmospheric component. So here we will have, looking at results from those two systems, we will have mainly the effect of increase into the atmospheric component, while the ocean should be pretty similar, at least for the large scale simulation, beside the effect of the winds between the simulations. Of course, I will show also comparison with observation. They are not listed here, but they are always indicated on slides. And also I would like to say that actually observation for this kind of study can be a caveat actually of the system, because when we increase the resolution into the model, we would like to interpret and validate model results against observation. For that, we need to have high resolution observation, but that's not always the case, mainly where we are in high latitude regions, as the one that we are going to talk about today, where the resolution of data is really sparse, still really sparse, and most of the record that we have cover really short periods close to the present time. So also observation for validating data can be a shortcoming of this study. What increasing resolution means for the ocean? That's pretty clear if you look at the North Atlantic plots that we have here. So those are velocity field at surface from the same model. It's a NEMO simulation with 3 different ocean resolution, the one that I showed you before. So we have the Orca 1, this name of the grid at the ocean. For NEMO, the generally Orca 025, what we call the eddy permitting ocean in the middle at 25 kilometers at the equator. And then we have higher resolution that I'm calling here eddy resolving, even though the name, the terminology is wrong, in the sense that the resolution here is 8 kilometers at the equator, and then given the shape of the dipolar grid used in NEMO, the resolution increasing, moving polarwards, but not enough to explicitly resolve mesoscale everywhere into the ocean. So generally, or at least correctly, we should call this kind of ocean configuration as eddy rich or edding ocean, because the mesoscale are not explicitly resolved everywhere. So if we stay even the mid latitude close to the coastline over the shelf, actually we are not resolving mesoscale because the Rossby radius is much smaller than the grid size there. The same if we move northward. So if you are into the Nordic Sea, so into the Arctic Ocean, actually we are probably resolving mesoscale only into the open ocean and partially into the open ocean, but not everywhere into those basins. But anyway, besides that, the benefit of the increasing resolution into the ocean velocity fields, it's pretty clear looking at these 3 plots. So we have kind of just a sketch of the large scale circulation when we look at lower resolution, while the large scale circulation is much better shaped with the proper Gulf Stream structure, and also boundary currents already shaped when we move in the eddy permitting simulation. Of course, all tropics are very energetic, and there are also a lot of mesoscale appearing into the ACC area, into the southern North Atlantic. things get much better, or at least dynamic it's more intense, stronger, more evident when we move to higher resolution. So the permanent eddies, for example, are well reproduced. If you look at the Gulf of Mexico, for example, there are a lot of mesoscale activities relating to the western boundary to Gulf Stream. The intergyre is really well shaped. So if you look at the extension, the zonal extension of the Gulf Stream is much more evident here than into the previous plots, but also the North Atlantic drift is well reproduced. And then if we move northwards, it's pretty visible that we are also resolving narrower and stronger boundary rim current, both the Nordic seas, the Labrador Sea, even into the Baffin Bay. It's easy to depict the rim currents. And of course, if we move into the Southern Ocean, all the typical or the real actually mesoscale activity is much closer in this simulation to the observed one compared with the previous. So we can easily believe from those plots that at least locally or at the regional scales, the mesoscale activity, so the finer scales into the ocean are better reproduced. And it's actually the case when we look at the upper ocean. But what happens when we move actually to the 3D global circulation, so the three-dimensional circulation that spans then the rest of the globe and connect the North Atlantic with the Pacific and the Arctic, and mainly with the dense water formation into the Southern Ocean. That is not part of this study. So how the improvement that we have into the ocean circulation visible from those plots into the upper ocean can be actually seen when we look at dynamics like the overturning circulation. It's key aspect of the climate dynamics, the densification of water at high latitude state would somehow forced the overturning circulation. The heat transport toward the Arctic, so the meridional heat transport into the North Atlantic is strongly linked with the mass transport, so with the MOC itself. And wherever, or if those three processes, so those aspects of the circulation are actually changed by the resolution, how that affects the higher latitude. So what happens into the Arctic Ocean, mainly what's the impact that we have on the decline of the Arctic sea ice there. So we can start with the meridional circulation. On this slide, you have the spatial structure of the zonal mean of the MOC computed in Sverdrup, and this is showing density space. So we have actually the MOC is function of latitude and depth. And what I'm showing here into the first slides are the control simulation. So here we have an average of the MOC computed over 15 years of simulations for all different model systems. On the left-hand side, you have panel where both atmospheric and ocean circulation have been changed, while on the right side, we only have system where the atmospheric resolution has been changed. The palette is the same for both cases. On the left column, there is always the high resolution MOC, while if you look on the right column and in both panel, you have the difference between high and low resolution. So generally, we can say that whatever is the high resolution modeling system that we are running, the structure of the MOC is pretty similar among different models. Of course, if you're going to look at details, that's not the case, but the general 2D structure is here reproduced in the sense that we have the warm and salty water that moves northward into the upper ocean, let's say the first kilometer of the ocean. The intensity it's really different among models. Then we have some sinking or whatever densification as we reach the Greenland-Scotland Ridge. So we are in the northern part of the basin, around 16 degrees north, and then more or less weaker deep cell that is going to close the 3D overturning. This is really changing among model. In some it's absolutely absent, even high latitudes. For some other resolution, like CEST, that is really high, is 1/10 of a resolution, start to be evident that actually there is some overturning is also into the deep ocean. And then if we look at the difference between high and low latitudes, then we see that there are only two models where it's evident that increasing resolution means also that we increase the overturning circulation. So for ECNWF, for the AGEM, we have actually large differences, is about 5-6 Sverdrup, mostly everywhere into the North Atlantic. There is no big change when we cross into the Nordic seas at even a higher resolution. There are few models where actually we are in the opposite situation. So for example, for the first case, we have Fairfax model that has slightly decreased into the hammock when we increase the resolution. That's also the case for the MPI that you will see it's always having strange behavior compared with all the other models. Here we only have increase into the atmospheric resolution. The ocean is fixed at 15 kilometers. And this is the only model where the structure is pretty similar if you move from one resolution to another, but the strength is much weaker when we increase the resolution into the atmospheric component. And then for the other two simulation that we have with the only changing into the atmosphere, there is a slightly increase into the hammock. So that kind of makes sense if we think about the impact that we had that we look at before looking at the upper ocean circulation. So everything gets more intense when we increase the resolution. We have more mesoscale. We intensify somehow the transport of volume northwards. So for when we see red into the difference here, that makes sense for what we expect. When we see blue into the difference, then things get a bit puzzling. To be more, let's say, to try to understand more in detail what happens into the overturning, one way is to plot, let's say, a more proper computation of the overturning stream function. So instead of using latitude and depth, we can use latitude and density. That helps to depict different classes of density where we actually have transformation of water. So to read those plots, it's pretty similar to what we saw before. So we have northward flow into the upper ocean that is not into the highest part of the plot here by relating to the high density, because that's salty and warm water that flows poleward into the North Atlantic. Then we have the densest water when we get closer to the 50-60 degrees north, so close to the Greenland-Scotland Ridge, where we have somehow sinking and convective processes. And then all the rest actually is representing the upper cell, mainly the Ekman cells that we have into the real surface circulation. So here it's more evident looking at the second the second column, where we have the difference between a high and low resolution, that the increase into resolution impacts the hammock, increasing the strength of the overturning circulation. There is again only one exception. There's still the MPI. So in this case, even if we look at the overturning in the more proper way, making the zonal mean of the velocity fields by into density space. Also in this case, we see that the overturning is decreasing, but because the density of the water that are formed into the northern part of the the North Atlantic, actually it's lighter. So that's absolutely counterintuitive, and we will see there's no clear physical explanation for that going through next slides. So generally, we have similar behavior among whole model. Of course, again, when we change the ocean circulation to the impact that we have it's higher, and it's always stronger around 1460 north, where we had, again, convection and densification, but also in the runs as the CMCC one, where there is only increase into the atmospheric fields, means that we have a colder atmosphere or more intense wind over the Labrador Sea. So somehow we can reinforce the convective processes into the area and have more dense water formation also in this simulation. One point I would like to highlight is the CEST simulation, because here we are comparing the 1/10 degree with the very low resolution 1 degree. So totally different regimes into the ocean. But actually what we see when we look at the dense water formation, so we should stay on this part of the plot here, there is not really large difference. So at least it's much smaller than the other simulation when the change into the ocean resolution is much smaller. That's because into the CEST low resolution model, there is ad hoc parameterization for the overflow. So on the mixing processes in the Labrador Sea and Nordic Sea, so at least across the reach connecting North Atlantic and Nordic Seas. So the difference that we have into densification, whatever is the resolution, it's really small. So the circulation itself is different, but this peculiar process relating to densification is really similar. So most of the difference that we have represented by this dark red are actually relating to the not to the dense water formation, but to the upper limb, pretty light, if you look at density, that is flowing northwards into the Nordic, into the North Atlantic toward the Arctic. If we want to validate somehow the results that we saw so far for the entire basin, one thing that we can do is to start to use time varying simulation. So here I'm showing not the control run as before, but the historical one. And we're using data for the first time. So here I have the rapid array also showing all the plots. So black line is the vertical profile of the AMOC at 26 degrees north as observation reproduced that. And then we have in different colors all the other model simulation with the set of resolution for both ocean and atmosphere. One point here that I forgot to mention before, they have, for example, two systems for the easy Earth identified by P2 and P1. That's because easy Earth within Primavera, beside the change that they have into the resolution, they also had actually changed into the physical setting of all the components of the model. So they're showing, at least in this particular slide, I have both of them, even though the quality of result is pretty similar. But then for the CMIP exercise, they use this P2. So we have, again, the simulation divided by changing both components, change only into the atmospheric component, then we have the very high resolution into the ocean for CMMs. Here also we have change for EC and WF in both components. What we can see that generally, if we increase the resolution, so we move from light to dark color, we tend to increase the maximum IMOC. That is generally well located in all simulation at 1 kilometer, as actually is done from observation, except for the two easy Earth simulation and also the CNRAM, where they all have a kind of shallower maximum for the EMOC at 26. They all have NEMO simulation, but that's the codes used also in other system. So it doesn't seem to be ocean dependent itself. And then if we look at the impact of resolution again, for example, if we go to the UK system, we see that there is no really large difference when we go from low to medium to high resolution. But then if we look at the orange line here, that's the very high system where they increase the resolution, let's say heading scales both into the atmosphere and into the ocean. That's the only simulation where actually this line follow pretty well the observation of the black line that represents rapid. If we go to the atmospheric resolution change, we see that there is really a large difference between CMCC and MPI simulation as we saw before, MPI is still puzzling because when we increase the resolution into the atmospheric component, actually we decrease the EMOC, also vertically that's visible at 26 degrees north. And actually the maximum is kind of comparable with the very low low resolution couple system typical, for example, by CMIP 5 exercises. If we stay close to the CMCC, we see that whatever is the resolution here, the ocean is at 25 kilometers at the equator, but here we tend to overestimate it over timing. It's the only exercise where we actually have that, at least the overestimation is that strong. Of course, it's also present somehow in CEST. And then I want to mark here that the ocean model is different into these two models, but again, they use common size, different version, but similar system. So that could be one similarity. Beside the difference, also into the resolution, one similarity among the system. If we go deeper, looking at the profile, so even though the upper structure is pretty similar to what we expect to see with the maximum at 1 kilometer, if we go down, actually the differences among models tend to get smaller in the sense that the results are much closer. So we have the most model actually cross the zero. So we reverse the cell of the overturning really at shallower depth compared with observation. So most of the model actually have very shallow EMOC limb on top, and around 2 or 3 kilometers we change to the deeper cell. There is only one exception, that's the CMCC, where actually we have the deeper part of the circulation. So the deep western boundary current is well located in depth, and also the intensity is pretty close to rapids. Then for other system, again, it's only the very high resolution that is reproducing also the deep cell pretty well into the UK system. Surprisingly, there is a wrong representation, now a misrepresentation of the deep cell also into the high resolution of the CEST system. So the circulation is quite intense, as we saw before, into the 2D structure of the EMOC, but the sides, the vertical structure of the cell is as wrong into the 1/10 of degree as into the low resolution simulation from other model. Actually, in this case, the resolution, the CEST low resolution is doing better job at 26 degrees north, at least comparing with the high resolution. If we try to explain the differences that we have among model here, we can start looking more in details to the vertical structure of the water column. So for example, here I'm showing the vertical profile, actually the bias of model compared with EM4 at 26 degree north as function of depth. So I have the black lines here, they are showing temperature and salinity from EM4. So that's the initial condition of the system, but also our reference here. And then we have the difference between any single model or ensemble and EM4 itself. So if we look at temperature, we can easily see that most models tend to be colder, close to the surface. Please note that actually the scale of depth is not uniform. So the upper layer is much larger than when we go deeper. So into the first 500 meters, most of the models tend to be colder. And there is again outlier, and that's the MPI, high resolution system. Then there is large similarity wherever is the value of the bias, at least into the shape of the profile among other models. And when we go deeper, most of the models tend to be colder. Let's say the thermocline between 500 and 1500 meters, warmer than the observation. Even though there are actually better comparison with some models, for example, UK system or HighRes resolution is pretty close to the observation. The temperature doesn't help a lot to understand the difference into the EMOC, but then if we look at salinity, that drives actually the conclusion that we had on density before. So if we look here, the vertical profile, we see that the model system or the simulation that presents very high overturning simulation at 26 are the one having very high salinity. So they tend to be much denser the observation, and that's the case for the bluish line. There are the CMCC simulation at both resolution. There's no really large difference among that. Again, the ocean is the same. And also for the CHESM simulation, both the higher resolution, the 1/10, and the non-eddy ocean, they are always saltier than observation. So that's for sure one indication that the North Atlantic tends to be denser. Wherever is latitude, then will be much more evident when we go northwards toward the Labrador Sea mainly. So tends to be denser the observation. While if we look at surface, the differences are varying much more, in the sense that there are models wherever is the resolution, they are fresher than observation. That can have an impact on long term on the meridional overturning, and some that are even higher close to the surface than observation. What that means in terms of now, before going to the Labrador Sea that I already mentioned, I would like to show that's the only plot where I have actually the response of the North Atlantic to future forcing. So here we are looking at the historical simulation, but also at the future simulation. So here we have the time series of changes of the EMOC in time. And those are calculated as the difference between the model simulation, historical or future, against the control run, divided by the control run again, from divided by the mean, the long-term mean of the control run. And the differences are expressed as percentage. So when we have negative value, that means that the historical simulation on the future simulation are actually producing a lower EMOC compared with the control run. And looking at the plot, you see that we have put together runs with similar ocean resolution. So we go from the low NEMO simulation here, low resolution NEMO simulation. We have MPI, we have the eddy permitting NEMO simulation, then we have the two outliers with eddying ocean. And then you can look only at the thick line that represents the single products for for a system where we have only one run available, or they represent the ensemble mean for systems like ECNWF or ECRT, when actually institution has provides many members. So just to remove the short-term variability, you can look directly at the tick line here, and you can easily see that, let's say, whatever is the resolution, we have kind of decline into the AMOC. That makes absolutely sense. Even though there are simulation like one of the low resolution ECR simulation, where actually, at least for the historical part of the simulation, we have pretty flat line, so the decline is really small. And
Dorotea, you still have 3 minutes.
Oops, okay. So even for the end of for the future, actually the decline is but only 10%. This number actually increase when we go to higher resolution. So we are higher than 20% when we are in the eddy permitting ocean. And if you go to the eddy ocean again, the CHESM has already puzzling results for the decline is pretty flat again for also in this case for the historical simulation. The decline it's really small even for the future, while the NEMO simulation goes down to almost 28%. I will try to go faster for the densification. So the mixed layer depth into the Labrador Sea and Nordic Seas. Of course, this kind of process is strongly relating to the AMOC and the transport, let's say the global thermaline circulation. What I want to show here that we have two data sets for reference, and Argo EM4, they are here computed for different time frame, but what we see is pretty similar. So we have higher mixed layer depth into the Labrador Sea and into the Greenland Sea, into the Nordic Seas. There is generally shallower than 1 kilometer. When we go to the model, we have low resolution, high resolution or eddy permitting ocean here, only atmosphere modification and the very high resolution. There is no CHESM here plotted. And then you see that generally we can say that increasing the resolution, we increase the densification, we increase the depth of the mixed layer. And that makes sense for what we said before and the impact that we saw on the AMOC. But that doesn't mean that actually the model are probably reproducing this particular process. If you look all this column, mainly the area and the depth of the mixed layer, it's always extremely higher than observation, both Argo and EM4. So this is the first, let's say, big shortcoming that we have out of the simulation. So the densification into it highlighted into North Atlantic, it's wrong, but has the nice effect, has good effect on the simulation of the overturning circulation. I can skip this one. I can go to the heat transport. Here we have the typical plot of the heat transport. So we have again the zonal mean of the transport of heat into the North Atlantic for all different model simulation. We have also how we introduced here. There was not present before because the intercomparison with the structure grid is really puzzling. So we didn't manage to make right conclusion. What you see here, that's generally when we increase resolution, we say we intensify the surface installations and we intensify the AMOC. So it makes sense that we have higher heat transports when we have increased the resolution. But even though if you look at the black lines and black dots, they are all estimates or observation, only the CMCC model can actually get closer to observation, while all the other model are for most of the basin underestimating those. Situation is slightly different when we go hit high latitudes. If we think about high latitude and we stay north of 60 degrees north, that means they were entering the Nordic seas and we are going into the Arctic. And there, the amount of heat that we move polarward has large impact on sea ice. So here you have the variability as seasonal cycle for the historical output compared with the black line, there is OSAF, so satellite observation. And then you see that also in this case, the changes among models is pretty large. For some models, we see that increasing resolution has a good impact on the oceanic transport is one of the main processes that affects sea ice decline. So if you look at the reddish lines, wherever is demand, we have actually the light color that goes closer to the black. But for other simulation like the CMCC, there's here gray also MPI, when only the atmospheric circulation is, the atmospheric resolution is modified, actually the impact is different. So increasing resolution, actually we increase sea ice. So for the atmospheric resolution, the impact is not clear, while for the ocean resolution, given the impact that we have on the upper ocean itself, is pretty clear where we see into the ocean. I can go back on that if you have a question on sea ice, and I would like to stop with the conclusion. So generally, we can say that wherever is the component where we increase resolution into the system, we somehow improve the results. But this is kind of really general and overall conclusion. If we look at single processes, as we show, it's really model dependent and process dependent. Most model can improve the AMOC and the heat transport when we increase the ocean resolution, while the impact of atmosphere, but that was also shown in previous study, is not that large. And mainly it's important when we think about the AMOC, think about the densification of water that actually is driving the strength of the hammock. That's for the wrong reasons, we have good impact over the overturning circulation, but actually the convection process itself gets worse into the model when we increase the resolution. There is nice impact on sea ice, at least on the decline of sea ice when we increase the resolution into the ocean. There is no clear effect when we increase the atmospheric resolution. I think I can stop here, Enrico. We can go with questions. The last slide that anyway I want to show is it's giving you indication of the publication where most of the results come from, and other publications, they are still on the North Atlantic large-scale circulation based on the same kind of simulation.
Thank you very much, Dorotea, for this really interesting talk. And there is a lot of information. And as you said, if people is interested, can contact you, I assume, also later on. But let me just start with the question. There is one question from Panos Athanasiadis that is thanking you for the talk, and also is asking if since there is the CMCC2 model that exhibits stronger than the observed AMOC, could you please comment what is the origin of this bias in your opinion? And also, do we see these also in the historical OMIP simulation? For the audience, OMIPs are the ocean-only model runs with atmospheric forcing fixed with the CMCC CM2 model. So why is the VHR4 model, the high resolution model of CMCC, worse than the HR4 model in representing the AMOC?
I wouldn't say it's worse. I would say it's different. So here, saying who is doing better beside the few models they are doing really well is pretty hard, because for, as I say, for some wrong reasons, things can get better into the simulations. For example, what is somehow different from the available observation into the CMCC simulation is actually the densification into the Labrador Sea, or at least the ocean circulation and the water properties, that means the density, temperature, and salinity profiles into the subpolar jar. That's mainly driving the high value of the MOC that we see. That's relating to the Orca 025, so it's probably, of course, it's depending on the ocean, but also what we see, that's the intensity of the wind and the temperature of the atmosphere in both simulation. It's kind of forcing or driving a lot of densification into the Labrador Sea and Nordic Seas. So I would say that into the CMCC model will be nice, and I know that you're going to work on that. It will be nice to actually to dig more into the interplay between the atmosphere and the ocean at high latitude into North Atlantic. I haven't shown anything on surface fluxes into for the simulation, but of course you have large effect when you change the heat transports and subpolar jet circulation. You have strong effect on surface fluxes.
Okay, so there is another question from Casey Patricio. It just arrived, and if I remember correctly, you showed that increasing ocean resolution leads to larger bias in the MLD in the Labrador Sea. Have you looked at whether this is associated with any bias in the variance of the surface heat fluxes of the sea surface temperature in this region?
Yes, for the couple simulation, things are absolutely related. And there are papers for Malcolm Roberts actually on that. The Labrador Sea changes that I show to Casey before with the resolution were actually done with another kind of simulation, still from CMIP exercise, but with fixed atmospheric forcing. And in this simulation, when we explicitly resolve the mesoscale activity into the Labrador Sea, we see that actually the ocean is playing most of the role in shaping and modulating the deep water formation, and wherever are the fluxes to the atmosphere. And most comes really from the eddy exchange of heat within the Labrador Sea.
Okay, so this is just curiosity from my side. Do you think that it is, assuming that we are going to continue to develop and to improve our models, in terms of looking at a better representation of the AMOC, would you suggest to still push in multimodal assessment at the higher resolution, increasing again and again the resolution in the ocean and the atmosphere, or do you have any other potential solution or suggestion for experiments that could be done in a multimodal framework that could help us in improving the AMOC representation in our climate models?
If the key topic of the intercomparison, the multimodal intercomparison, as you mentioned, is the overturning circulation, from my point of view, that means the ocean point of view and mainly the high latitude processes, I will say that increasing the atmosphere resolution, at least on these scales that we have seen here, is not particularly relevant, while increasing even more the resolution into the ocean could make the difference. One key point is that, of course, the resolution cannot answer all the questions that we have. And for sure, working at those latitudes, mainly when we relate to the Arctic, have a better physics for sea ice. It's absolutely a key point. So having a good export of solid ice out of the Arctic into the Labrador Sea can absolutely affect the AMOC in the end. And all these, we know that all these processes for also the snow over sea ice are really still weak represented into these systems.
Okay, so the last quick question, because we are over with the time. Thanks for the presentation. This is from Vincenzo De Toma, and he's asking, it seems that most of the model tends to overestimate the mixed layer depth in the Labrador Sea compared to the Argo and the EN4, but increasing resolution seems to bring, in some cases, to improvement. What do you think are the still missing places in modeling we need to improve the mixed layer depth representation?
Actually, in this particular case, we see no specific improvement when we increase the resolution. So here we have the low resolution, and here we have at the permitting ocean a higher resolution, an intermediate resolution into the thermosphere. And all these cases we have the wrong effects on densification and convection sides. The reason for that is actually known into the model system. So then one key point, sorry, that probably I never mentioned is that whatever we did here on the resolution is only on the horizontal resolution, while those processes, mainly what we're looking here into the LabDRC, is strongly relating to the vertical resolution. That is pretty low in all this system. Even when we have adding rich ocean, the resolution is really weak. So I wouldn't say that there is actually an improvement into the mixed layer and convection events when we increase the resolution. It's all wrong here, but the effect on that is that the mixing, the diapicnal mixing into these oceans component that we are looking here is misrepresented at the permitting resolution. And again, to have some benefit, we have to go to this kind of resolution. So we have to really resolve mesoscale explicitly, or to have the right parameterization, that's not the case yet, into the LabDRC and Nordic seas.
Okay, thanks a lot again, Dorotea. And for any other question or clarification, please do not hesitate to contact the author. So time is over. Goodbye, everybody. And don't forget the next webinar in 1 week.
Enjoy
Thank
your
you again,
lunch.
Dorotea.
Ciao.